So let's see what happens when a file is deleted from the FAT file system and how you would go about manually recovering that file. Recall that from our last class that under a file allocation table file system that the root directory entry holds the starting cluster of the file and that the FAT is a singly linked list of clusters that comprises the file. So essentially two simple things happen when a file is deleted. The first is the root directory entry is marked as available with a hex character E5, which is also called a sigma, and the FAT entries are zeroed out, indicating that they are available for use. So what doesn't happen? First, the information comprising the file is not removed. It will remain there ad infinitum until the operating system needs that room and then will overwrite the file. Also, the root directory entry remains until it's overwritten. So this could last for a very long time. So when somebody thinks that they're deleting a file, that's not necessarily the case. But the longer the operating system is on and the file system is up and running, the longer there's an opportunity for the operating system to overwrite the root directory entry as well as the contents of the deleted file. So before we start talking about how to manually recover a file, let's go in and let's delete a file. So the first thing we want to do is we want to see if our floppy is mounted. And we see that it's not, so we need to mount that floppy. Okay, and we type mount to see if it's mounted, and if we look at the bottom, we see that it's mounted on floppy 0. Type vfat, it's mounted read-write, no execute, no SUID, no dev, user equals PC. No execute, meaning there's no executables are allowed to execute from that, or no SUID, root files to be run from there as well. Okay, so let's see what's on that disk. There's two files, 1.txt and 2.txt, as we saw before. Notice their sizes. The first one is 312, which means it fit in a single cluster. The second one is 770 bytes, which meant it had to fit in two clusters, but we saw that previously. Let's clear that. And very quickly, let's go back and take a look and see what those root directory entries look like. And we're going to scroll down to 2600. Here we go. And we see on the right-hand side of the ASCII section, it's got 2.txt is the name of the first file, and 1.txt is the name of the second file. So what's going to happen? Well, when we're going to delete one of these files, let's delete 2.txt. What's going to happen is that first T is going to change to a sigma character, an E5 in hex, and we'll be able to see that clearly. So what we're going to do is we're going to remove media, floppy, 0, 2.txt. Sync. Okay, let's go back and take a look at what we've got there. Here we go. Now look at the first character in the hex section. Note that there's an E5 there. That means that the root directory entry is available to be reused. If we go to the right-hand side, notice it has a dot there. And so, interestingly, from that, we can't recover the original name of the file, the first character. If we go back to the first FAT, and if you see what happened, if you recall from the last class, if you look at hex 200 there on the left and scroll over, there was a 03 in there indicating that at the second cluster and the third cluster were being used for the for that file, 2.txt. That's no longer there, that 03 in the 02 cluster position. And the reason is because that is now telling the operating system that that file is able to be used if need be. So if we go to the data area though, wow, the file is still there. The entire file is still there, as you can see. And so Those are essentially the things that occur when a file is deleted under the FAT file system, but it's pretty much the same under all the file systems, is that the data will remain until it's overwritten. So how would we go about manually recovering a file? For those of you who've used recovery utilities, you can imagine what this is going to show is generally how these are working, because they need to know a few things. The first thing they need to know is the starting cluster of the file and the file size. If I know the starting cluster and I know the file size, I can recover everything from the starting cluster all the way to the end, and I've essentially recovered the file manually. And we can do this with DD. What a great utility that is. This is just showing some deleted files right here. Notice that there's recall that each root directory entry is 32 bytes, which means it takes up 2 lines. And so there's an E5 right here. Notice that there's a period here, unprintable character. And if we go down to here, here's another one, and here's another one, and another one, and another one. So it looks like all these JPEG files have been deleted. However, if we look over here, where the starting cluster is for each of these files, that information is still there. Not only that, but the file size information is there. Starting cluster and the file size. So we can actually go in and actually recover these as long as their contents have not been overwritten. Do we know if it's been overwritten? Well, we actually don't know. What it's best to do in this case would be to go in and manually recover these and see if that information is still there. And so here what we're going to do is we're actually going to walk through an example of how this works. So if we look back here, we see that this first file is something 392.jpg. Okay, so let's recover this file. Notice that here is the starting cluster and here's the file size. Recall from last time, because we have 1.5 bytes, byte swapping is, we have a packed bit representation of these locations. What we need to do is do some byte swapping in order to recover the original location. So here we see we have the starting cluster 7F01 and the size is A07D. Okay, and so what we're going to need to do is we're going to need to swap this around in order to recover the location and size of the file. What we're showing here is the fact that by actually going in and changing the starting cluster here to is actually doing the byte swapping, we can actually go down and find the start of the file, which ends up being here. And notice that we have several bytes, 1, 2, 3, 4 bytes here, FFD8, FFE0. Well, it just so turns out that right there is actually the header for JPEG. Well, recall this had a JPEG extension, which means that we know that at least part of the file is still available. Okay, so let's manually do this. So the procedures: find the starting cluster, find the file size, and then extract the contents of the image starting at the starting cluster, and voila, hopefully you've got something. So for this example, we're going to do a byte swap. So byte swapping this, we're going to move this here, right here, and essentially what that ends up doing is that we've got this actually translates to 17F. If we put this in a calculator, in a decimal and hex calculator, essentially what you're going to do is you're going to type in 17F and make sure that the calculator is on hex, and then hit the decimal and it will change this to 383. This will be the starting logical cluster. Okay, recall that there were, if we added up the size for the boot sector, the FATs, and the root directory, it came up to 31. That's the reserved area. Okay? And so if we take the 383 plus the 31 equals 414, which is the physical cluster. And then if we multiply 414, the physical cluster, by the number of bytes per sector, we get 2111,968, which means the byte offset is 33C00. And if we go back here It's essentially what we've seen here. So we know, based upon the contents of the root directory entry for this file and the fact that this has a JPEG header, is that we're looking at the file that we want to recover. The next thing we need to do is we need to calculate the file size. So if we do the byte swap on A07D, this becomes 7DA0, and then we put the 7DA0 in our calculator on hex, and we type this in, and then we hit decimal, and it changes to 32,160. Then we can divide that by 512, and so we see that this file is going to take about 62.8 K, or about 63, or excuse me, sectors, 62.8 sectors, or about 63 physical clusters or sectors. And remember now, the reason I'm using sectors and clusters interchangeably here is because we're talking about a floppy. And on a floppy, the sectors and clusters are of the same size. Now, having known that, what we can do is just go in and recover the file. And so we're going to type dd, the input file equals our image, because we've taken an image of the file, and our output file is going to be underscore 392.jpg, which is our recovered file name. We're going to skip to 414, okay, because that's where it started. Let's look back here. It's sector 414. And then we're going to count for 63, because this is what we need. If we said 62, we wouldn't be counting all of it, because it actually is composed of 63 physical clusters. And so we did this. Here we have 63 records in, 63 records out, which should be about 33 or 32K, and that's a recovered file. That is our recovered file. That was the deleted file. Okay, so now we've got this information. Let's go about calculating where it starts, where the file starts, and how large it is. So the first thing we see here is we have 0200. Let's go back here and see the procedure for the byte swap. So essentially we've got 0200, so this starting cluster is going to be 2. And so it's 2 in hex, so we're going to need to convert that to the decimal. So let's go over here, and this is really silly, because what do you think it's going to be? So hex, decimal is, wow, it's 2. Well, could have told you that. But just to show you the point, now we need to say the reserved area is 31 sectors, so we need to add 2 to the 31, which is going to give us 33. So that's our physical cluster. And so we take 33, multiply that by 512, the sector size, and that gives us our byte offset. And so we're going to have 31 plus 2 equals the 33, and then we're going to multiply that by 512 equals 16,896 in decimal. In hex, if I click this, what's it going to be? I'm guessing it's 4,200. Right again. Okay, so we know it starts at 4,200, but we had already kind of figured that out. Now let's do the size of the file. So we need to go back here. We'll see the size of the file 0203, and notice that there's all zeros over here, so we need to convert this. And we need to do some byte swapping, which is going to actually be, we do the 3 in front of the 02, and so we're going to have 302. Okay, so 302 in hex, and then we're going to change that to decimal. Okay, now what's the sector size, the cluster size? It's 512 divided by 512 equals 1.5. Okay, so we're going to need about 2 clusters, 2 sectors to grab that file. Okay, so let's go back here, and now we can use our dd input file equals what? Input file equals floppy. dd, the output file equals underscore wo.text, and then we're going to count for equals 2, and we're going to skip to 33. Skip equals 33. That was our physical cluster offset. Now let's hit enter. 2 records in, 2 records out. 1024 bytes transferred. Why is it 1024? Because our default block size for DD is 512. Remember that from last time. Okay, now let's go in and let's take a look at this file. There it is. What are those funny things at the end? Well, remember we recovered everything all the way to the end, so we're actually recovering information in there that is of a non-standard printing character. But notice that everything else we've actually recovered the file. So as you can see, that is a very easy way to recover a file, and you should practice this on your own. I would say go in and save 2 or 3 small files to a floppy, delete them, and go in and use the various manual methods to go in and to recover those. Realize one thing though, that if a file is fragmented, then this will not work. It will not work, because then what essentially you'd be doing is you'd be recovering files from they're contiguous within the file system, however they're actually from different files. So this can only really be used when you've got files that are contiguous and not fragmented.